Welcome to the debate. Our focus today is on the physical chemistry of alkyl halides. So, we're talking about molecules where a carbon atom is bonded to a halogen, what we call Rx. And the foundational chemical fact here, really the starting point for everything, is the polarization of that carbon-halogen bond. It's just an inevitable consequence of the halogen's higher electronegativity pulling electron density away from the carbon.
Right, and that core polarization is absolutely what gives the alkyl halide its identity. It distinguishes it structurally, electronically from its parent alkane. But our discussion today, I think, centers on a really critical tension. When we look at the macroscopic, measurable physical trends, things like boiling points, density, which influences truly defining the behavior of this chemical series? Is it that inherent electrical definition, the permanent CX dipole moment? Or is it the overwhelming additive effect of mass and size, which we see through van der Waals forces?
And I'll be arguing that for the most crucial physical properties, especially those related to phase transitions, the trends we see are overwhelmingly governed by these mass-dependent van der Waals forces, specifically London dispersion. Polarity, sure, it provides the initial definition, but I think mass and size are the variables that really determine the magnitude and direction of the critical changes we observe. I'm firmly on the side of van der Waals dominance.
And I'll be taking the opposing view. Look, no chemist denies the influence of van der Waals forces, of course not. But I'm going to argue that the permanent CX dipole moment is the foundational characteristic. It establishes the unique structural and electrical parameters of the bond. It dictates how the molecule interacts with its environment, and it reveals complexities that are completely independent of just a simple increase in mass. For me, polarity defines the class. Mass merely scales the energy required for a change.
Okay, so let's start with the clearest piece of evidence, which has to be boiling point. It's the ultimate gauge of intermolecular force strength. For any given alkyl group R, the boiling point trend follows a strict, really unambiguous order based purely on the atomic mass of the halogen. It always goes R iodide is greater than R bromide, which is greater than R chloride, which is greater than R fluoride. There's no deviation there.
That is factually correct, yeah. The trend increases with molecular weight.
And this rise in boiling point is dictated entirely by the increase in size and mass as we move down the group from fluorine to iodine. So why is this so dominant? Well, it all comes down to polarizability. As the atoms get larger and heavier, they have a greater number of electrons, and these electrons are held in larger, more diffuse clouds farther from the nucleus. This makes that electron cloud way easier to distort or polarize, and that leads directly to significantly stronger instantaneous dipole-induced dipole interactions, what we call London dispersion forces. And this is not a subtle effect. I mean, look at the data for the methyl halides. They're the simplest set. Methyl iodide, CH3I, has a boiling point of 42 degrees Celsius. Compare that to methyl fluoride, CH3F, which is at minus 78 degrees Celsius. That's a staggering, 120 degrees Celsius difference in the energy required to overcome the attractive forces and enter the gas phase. This huge disparity proves that the mass and size effects from van der Waals forces just utterly overwhelm any slight influence of the halogen's electronegativity or the permanent dipole. If polarity were the defining feature, we would expect a much flatter curve, or maybe even an inverted one. Instead, we see absolute, almost linear dependence on mass and size.
Is that magnitude? I do. But I think focusing solely on boiling point lets you sideline the very definition of the compound. The van der Waals forces certainly dictate the magnitude of that boiling point increase, that 120 degrees of energy you mentioned, but the intrinsic character of an alkyl halide rests on the CX bond polarity. And this polarity introduces structural characteristics that are decidedly not mass-dependent. For instance, if we examine the fundamental property of the bond itself, the dipole moment, we discover a really crucial and non-intuitive trend. It speaks directly to the complexity that's inherent in this bond. The dipole moment mu, it follows the order. C iodide is less than C bromide, is less than C fluoride, which is less than C chloride.
Right. The fact that the CCl bond shows the highest overall polarity, even though fluorine is the most electronegative element, that's certainly the most cited structural anomaly in this series.
And I think it's the most defining characteristic. The C-Cl bond exhibits the highest dipole moment, which we measure into pi. This inversion, the fact that CCl is greater than CF, is so critical because it arises from a sophisticated interplay of factors that mass alone just can't explain. We have to remember that the dipole moment is the product of the partial charge delta and the bond length d. Mu equals delta times d. So while fluorine creates the highest partial negative charge, the delta, its bond length, the carbon, is very, very short. As we move to chlorine, the decrease in electronegativity, and thus the partial charge, is more than compensated for by the significant increase in bond length. This precise structural and electrical balance, this is what defines the bond's unique electrical character. This foundational, non-mass-dependent complexity is what truly defines the alkylhalides as a chemical class.
I appreciate the nuance of the charge distance calculation. I really do. But if we return to the physical reality, the polarity argument immediately starts to break down. If polarity were truly the defining factor governing the physical behavior of these molecules in the aggregate, then we would absolutely expect the compound with the highest molecular dipole moment, methyl chloride, to exhibit the highest boiling point, or at least a BP higher than its lower dipole cousins.
And its molecular dipole is significant. Methyl chloride is at 1.94 dBi, which is substantially higher than methyl fluoride at 1.82.
Exactly. Yet methyl chloride boils at minus 24 degrees Celsius, while methyl iodide, which has a much lower permanent dipole moment, boils at a balmy 42 degrees Celsius. The fact that the mass-driven boiling point trend completely overwhelms and frankly overrides the dipole moment trend proves that for phase transitions, the macroscopic behavior we are studying, the bulk effect of mass and size is just overwhelmingly dominant. Polarity gives it an initial boost above the parent alkane, sure, but it's relegated to a minor correctional factor when you compare the halogens against each other.
See, I just don't buy that the complex interplay of charge and distance, which results in the highest permanent dipole residing in CCl, is merely a minor correctional factor. This anomaly isn't a failure of polarity. It's a structural detail that distinguishes the series and dictates the potential for interaction and, down the line, chemical reaction. You are focused solely on the total energy requirement for vaporization, which is, yes, always going to be maximized by the molecule with the most electrons, the one with the strongest van der Waals forces. But polarity governs the type of interaction. Let's look beyond simple monohalides for a second to polyhalogenated compounds. We observe that boiling points increase systematically as we replace hydrogens with chlorines. CH3Cl is the lowest, then CH2Cl2, then chloroform, and finally carbon tetrachloride. Now, while mass is certainly increasing, this rise in boiling point is specifically attributed to an increase in induced dipole and dipole attractive forces. The growing number of highly polar CCl bonds facilitates these sophisticated interactions far beyond what a simple increase in molecular weight would suggest. This confirms that the complexity introduced by polarity is what's driving the interaction mechanism in these systems.
That is a compelling point about the progressive increase in BP through the chlorinated methanes, but I would argue that even carbon tetrachloride, CCl4, which is nonpolar overall because of its tetrahedral symmetry, it still has a high boiling point primarily because of its sheer molecular size and the immense polarizability you get from 4 large chlorine electron clouds. The mass argument holds up even there.
But we see a sensitivity to structure that's directly connected to the placement of that polar bond. Let's pivot and consider isomerism, a phenomenon tied entirely to molecular shape. When we compare constitutional isomers, molecules with the same formula but different shapes, branching causes the boiling point to decrease systematically. Tertiary haloalkanes have lower boiling points than secondary, which are lower than primary.
That's true. Tertiary has the lowest boiling point.
Right, and this happens because branching reduces the surface area available for effective dispersion forces. So this shows that the efficacy of the van der Waals mechanism itself, the one you're championing is dominant, is highly dependent on structure and shape. which are dictated by the geometry imposed by the alkyl group that's attached to the defining CX polar bond. So the structural decisions that stem from that central polarized bond fundamentally control how the van der Waals forces even operate.
I see why you highlight isomerism, but let me offer a different perspective. I'm not convinced that branching is evidence for the primacy of polarity. That decrease in boiling point due to reduced surface area, that's a general principle of van der Waals forces that applies to any molecule, alkanes, alcohols, you name it. It's a mechanism common to all polarizable species. It's not a feature that's unique to CX polarity. To assess what is truly defining, I think we should focus on physical effects that are uniquely defined by the sheer difference in atomic mass, an effect that truly separates the series. So let's turn to density relative to water. This property is fundamental, but it's often overlooked. Our bromides and our iodides are definitively more dense than water. If you put them in a beaker, they sink. On the other hand, our fluorides and our chlorides are generally less dense than water. They float. This fundamental binary separation, sinking versus floating, is a pure and undeniable function of the atomic mass of bromine and iodine. It confirms that mass dictates a major physical separation behavior that polarity just fails to consistently influence across the whole series. If polarity were defining, you might expect them all to have similar density patterns, but they don't. Mass creates a clear dividing line.
That density boundary is compelling evidence for the importance of mass. I'll grant you that. It illustrates the cumulative effect of a heavy atom. However, the definition of the alkyl halide series is still rooted in polarity, and that polarity leads to specific energetic limits, which brings us to solubility. If we follow the principle of like dissolves like, well, alkyl halides are polar, so they should exhibit strong water solubility, but we know they are at best slightly soluble or functionally immiscible in water. Their dipole moment, while significant, is simply insufficient to overcome the cohesive forces of the solvent.
Precisely. If polarity were truly defining this physical characteristic, its very presence should guarantee solubility in a polar solvent like water. But the source material states clearly what the limiting factor is: the energy released by forming new dipole-dipole attractions between the haloalkane and water is just not strong enough to compensate for the energy required to break the strong, directional hydrogen bonds within the water network. This inability to overcome the solvent's cohesive strength renders the permanent dipole secondary in this crucial fundamental property. It's a failure of the dipole interaction to compete with the bulk forces of the solvent.
That's a compelling line of reasoning, but I think you're misinterpreting the role of the CX bond here. The solubility issue isn't a failure of polarity, but rather the precise definition of the alkyl halides interaction boundaries. Alkyl halides are unable to form hydrogen bonds with water because the halogen atom lacks a hydrogen atom directly bonded to it. This structural limitation, combined with the specific moderate magnitude of the permanent dipole and its associated van der Waals forces, forces that are not strong enough to disrupt H bonds, but are strong enough to facilitate dissolution in organic solvents, that truly defines their specific physical interaction profile. The polarity dictates that they have an intermediate character. They are definitely soluble in nonpolar organic solvents, confirming like dissolves like in the context of intermediate polarity. The magnitude of the dipole defines the boundary condition. It ensures solubility in one environment, while its specific structural limitations prohibit it in another. It's a defining feature of the chemical class to have this specific lack of hydrogen bonding capacity and the resulting solvent profile.
So, to summarize my position, the permanent CX polarity is necessary to differentiate haloalkanes from simple hydrocarbons. It provides that initial electrical character, fine. However, once we compare the members of the series against one another, the subsequent, observable, and I would argue defining physical trends, particularly the order and magnitude of boiling points, are overwhelmingly governed by mass-dependent van der Waals forces. This is demonstrated by that extreme BP differential between R iodide and R fluoride, and it's reinforced by the clear separation we see in density relative to water. The electrical definition, in the end, is subordinate to the bulk physical properties defined by mass.
And conversely, I would maintain that the unique, complex nature of the CX bond characterized by that nonlinear dipole moment trend, where CCl surpasses CF due to the precise balance of charge and bond distance, remains the essential characteristic defining the chemical class. This structural complexity controls the boundaries and mechanisms of its physical interactions, such as its crucial inability to form hydrogen bonds, its sensitivity to structural isomerism, and its reliance on specific induced dipole forces to explain polyhalogenation trends. Polarity sets the stage and dictates the rules of the game. Mass is simply the power multiplier.
Well, it's clear that focusing solely on one type of force leads to an incomplete picture. We're examining properties that really rely on the total cohesive energy.
Absolutely. Both dipole-dipole interactions and the highly relevant van der Waals forces are necessary, and they work in a complex concert to fully explain the entire range of physical properties displayed by alkyl halides. We can conclude that appreciating the complexity of molecular forces requires acknowledging multiple, sometimes contradictory, perspectives to truly understand the interplay of structure, charge, and mass in these fascinating compounds.